Okay, so let's continue our discussion on the thermal treatment, which we have been talking about in the last two videos. And so if you look at like what we were talking about in terms of the different technologies, incineration, combustion being the most popular technology which is being used. We talked about the concept, the kind of how the waste to energy is being developed within the Indian context, and some of the issues that we should be careful when we are trying to go for waste to energy plant. It can work, but again it's a proper homework for that. So continuing that discussion, let's look at in terms of when we talk about this combustion. As I said, it's an oxidation process. So combustion is an oxidation process, and the amount, the fraction of the garbage which will actually go through the combustion is the volatile solid fraction. So this the volatile solid fraction, when we look at the volatile solid, we are looking at it's essentially the stoichiometric combustion is there. So we are looking at So we are looking at this stoichiometric combustion, where the volatile solid fraction, we have essentially carbon, hydrogen, oxygen, nitrogen and sulfur. So that will be what in the volatile solid part. So under ideal condition, what will happen? Under ideal condition, we'll have all these reactions taking place. So carbon will get converted to CO2, your hydrogen will get converted to water vapor, and water content of the flue gas, it will be part of that. Oxygen, of course, oxygen will actually help in the combustion process. Nitrogen will be there. Usually at the temperature at which we work, we don't have this NOx being formed. And then sulfur will get converted to SO2. So these are the ones you see that what will happen. So it's a small amount of sulfur dioxide, mostly carbon dioxide, some water vapor. So oxygen is required. So we need oxygen for producing, for the burning the carbon. We need for the burning of hydrogen, and minus the fraction that enters as H2O. So there is some hydrogen already there, there are some oxygen already there. Then also for sulfur, we need the oxygen. So oxygen is needed for this combustion process. So when we say stoichiometric, we are basically trying to say from the very first principle, as you may remember from earlier chemistry and other classes that you had, that if you like a 1 mole of oxygen will react with, if you look at 1 mole of carbon will react with 1 mole of oxygen, and then of course there is some heat, and then you will get the CO2 produced. Similarly, hydrogen, 2 moles of hydrogen reacts with 1 mole, 1 mole of sulfur reacts with 1 mole. So again, these are very simple, just going to very basics that you had in some sort of high school chemistry. So if you know the formula, the question is to know the formula of this volatile solid part. We can calculate how much oxygen will be required, going by this stoichiometric, based on how much carbon is there, how much hydrogen is there, how much oxygen is there, how much nitrogen and sulfur is present. So based on that, we can calculate how much total oxygen will be required. So that's it's in terms of this, so that's what is known as a stoichiometric combustion, where you go by kind of the basic principle. So if you take one example, so if you assume that dry air contains 23.15% of oxygen. So we have this dry air, 23.15% of oxygen by weight, and then the amount of air required. So if you think about that amount of air required for oxidation of 1 kg of carbon, so we can do that math. 1 kg of carbon, so that means we can convert that into moles. So you divide it by 12, and then you get this much moles of carbon. So 1 mole of carbon will require 1 mole of oxygen. C plus O2 is CO2, and that oxygen is an O2. So we are looking at 32 grams per mole. So that's your, since it's both are in gram, it's okay, although this is in kilogram, since it will cancel out. So we are okay. Otherwise we can convert that to kilogram. We can convert this also to kilogram, and that factor will cancel out anyway as well. So with this we can find out how much oxygen will be required, and from how much 23.15% of oxygen is there in the air. So we can find out how much air will be required. So we get a value of 11.52 kg of air. So it's similarly you can do it for hydrogen, you can do it for sulfur, and you can find out how much kg of air you require for 1 kg of carbon, 1 kg of hydrogen, 1 kg of sulfur. So if for 1 kg of carbon require 11.5 kg of air. So it's actually for each one of them the number is higher on the air side. So because So that's we can do those calculations using the basic stoichiometric combustion equation. Now, stoichiometric combustion is the amount of hydrogen. First, we have to adjust the amount of hydrogen because like 1/8 of the percent of oxygen will be initially from the total percentage because of the water that whatever is the oxygen is present. So we can subtract 1/8 of the percentage of oxygen. The hydrogen for the hydrogen will first be adjusted by subtracting 1/8 of the percentage of oxygen from the total percentage of hydrogen initially present. That's to this subtraction account for the oxygen in the waste combining with hydrogen to form water, because this is there because water is what 2 grams per mole of hydrogen, 16 grams per mole. So that's why it is 1/8. So that's why it is say 1/8 over there. So since 1/8 of the percentage of hydrogen for oxygen is part of the hydrogen which is there as the form of water. So we need to take into account that part. Total oxygen, then the total oxygen can be then be converted to total air. We can do that. This calculation we are looking at the exact stoichiometric amount of oxygen or air needed. Many times we apply some excess air, because when you supply the air, here again we have to supply the air, like in the compost process we have been supplying the air for aerobic degradation. Similarly, here in the combustion process we are supplying air for the burning. So it's again it's a combustion is an oxidation process, so we have to supply the air to it. So when we supply the air, there may be some leakages, your things may not work up to 100% efficiency, so you always have some excess air. So that's what here we are talking about, that we supply some air as an excess of the stoichiometric amount. That's called the excess air. And why we do it? This is to make sure that complete combustion occurs, because many incomplete combustion leads to PAH, leads to carbon monoxide, even the particulate matters. If the combustion happens very nicely, if it burns really well, the pollution is less. So as you can see that initially also, like if you are even burning coal or you are doing anything, you are burning anything, once the fire really catches nicely, you don't see any much smoke coming out, even from your, if you burn some coal, or even if you said burn some stuff for a like campfire or anything. Once initially you get all those smoke, and then you get your eye is itchy and all that because of all the smoke coming out. But once it burns really well, once the really nice fire has set up, the smoke goes away. So because now the complete combustion is happening, the combustion so it's the smoke is gone, but the smoke is there but at a very low level. But initially when you have the incomplete combustion, you have lots of air pollutions happening. So excess air is usually we produce 120 to 200%. We don't want too much of an excess air. But earlier I said that when you work this incinerator, you work at a certain temperature. If you add too much of an excess air has a cooling effect. So temperature will try to go down, and the temperature goes down, you have problem in terms of creating more air pollutants, because the air again you have to, for formation of less air pollutants, you need to keep the temperature at a high level. So that's also is needed. So excess air is the objective of combustion is to complete destruction. So we want complete destruction. So to avoid our like a air pollutant issue. So for the complete destruction of the organic waste into harmless gases. So combustion process needs excess air. Why? Because we have a non-homogeneous mixture. Had it been a very nice homogeneous mix, the excess air requirement may be less. But here think about the garbage. One piece could be this small, the other piece could be this big, and then this may have this will burn really well, this may not burn that well, it may be more complex, the reaction will take longer time. So for all those things to happen, you need to make sure that you have enough amount of oxygen. And of course we do a lot of tumbling and turning, and we'll talk about that. And but those things are required because of the non-homogeneous. But as I said, too much oxygen, we don't want too much oxygen, because that will reduce the combustion temperature and that will lead to air pollution issues. So we don't want that. So in terms in terms of the excess air, then this term is very important in terms of air like thermal combustion especially. There are 3 T's of combustion. Like that's kind of the very basic of a waste combustor. You need to design it for 3 T's. Now what are those 3 T's? Number 1, temperature. We kind of talked about that a little bit already. Now why temperature? High enough to ignite, you have to burn it. Less than 790, if I just take it off, less than 790 will cause odorous compounds are released. You don't want less than 790 degrees. Greater than 980 and we get reduction in dioxin, furans and VOCs. So that's why I said most of the incinerator will try to work at around 1100 to 1200 degrees centigrade. Definitely above 1000. Because they want a reduction in dioxins, furans and VOCs. You don't want these to be released into the atmosphere. So they try to work at around 1100 to 1200 degrees centigrade, definitely above 1000. You will not see a waste incinerator working under 1000. If it works under 1000, that means it will have it may have a bigger air pollution problem, and then it will have a bigger load on the air pollution control system. Now that's the temperature, one of the most important, because temperature at high good enough for burning to take place and good enough for keeping the air pollutant low. So that's the reason why we look at the temperature. The second part is time, because it's a reaction, isn't it? You have done this chemical kinetics as part of your high school, or also maybe first year of engineering, first year of whatever discipline you were there. Whenever you talked about this chemistry, you talked about this chemical kinetics. Now what is this chemical kinetics? It basically tells you the reaction rate. Some reaction is slow, some reaction is fast, and effectively it takes time for reaction to take place. Reaction does not happen instantaneously. Some does, like if you drop a drop in, if you have a water and drop an acid and the acid really dissolves, and then you measure the pH at any point of there, it is okay, it will you will find the same pH. But if it's the lake was much bigger, probably not. But if I'm talking about a small beaker, yes. But same thing, but that's a liquid media. Things does dissolve and makes that reaction is relatively faster. But when we talk about waste incineration, we have the combustion going on. Things has to burn, so it takes time. So we have to know the time that it takes for reaction to take place, because when you will see the combustion chamber and you will see some sketches, the waste actually goes through the combustion chamber, so it gets dropped and then go through the grates, and then at the bottom it comes out as the ash. So the time it takes to travel here should be more than the time it requires for the reaction to take place, for the complete combustion to take place. Otherwise you will have the incomplete combustion. Your bottom ash quantity, residual quantity will go up, and you will be losing the energy that you could potentially get out of that. So that's why enough for complete combustion. That's very important. We need to have the complete combustion in the combustion chamber, and then also we do it in the flue gas for the secondary chamber. For the flue gas is also burned in the secondary chamber. So that's the in terms of the temperature, time. So 2 T's we covered. Now for the third T is what is known as turbulence. Now what is this turbulence? It's basically you are mixing. You are trying to mix the waste together. So you are trying to mix the waste together so that where the air comes in, it gets mixed, all the different areas gets exposed nicely so that it burns really well. So why it is needed? Again, it's for the heterogeneity of the material. It's otherwise it provides good mixing to promote more complete combustion. And we do it for both in the primary chamber and for the MSW, and then the flue gas which is released, which is burned in the secondary chamber. You will see some sketches that there also we try to mix them. So mixing helps in reaction. Is basically we are trying to make the reaction as complete as possible. So 3 T's, remember that: temperature, time, turbulence. So these are very, very important in terms of our combustion process, in terms of the waste incineration process. And in fact, this is also important for coal when you do this coal-based thermal power plant. But some of this may, like it for especially for turbulence, may be less in coal than in here, because that's a more homogeneous material. So we can do this. We can do this excess air calculation. There is a theoretical oxygen requirement can be determined by balancing the chemical equation. So if you know the chemical equation, you can just balance the equation. There is a if you do this, if you take any like a chemical formula for the volatile solids, if you know the carbon, hydrogen, sulfur, oxygen, you can also use this relationship which has been developed using the stoichiometric calculation. So if you can do it from basic as I showed you in few slides back, and or you can use this equation as well, which is then oxygen in meter cube per kg fuel can be calculated based on 24.6 times carbon by 12, hydrogen by 4, sulfur by 32, and oxygen by 32. Why oxygen is negative? Others are positive, but oxygen is negative. If you should always, whenever you see something like that, things should come to your head. Why it is this? Of course, it's very simple, because oxygen, the amount of oxygen present in the garbage, in the volatile solid fraction, will also contribute to combustion. They will actually act as an oxygen source which is needed for combustion. So that oxygen we are subtracting, because we don't need that oxygen is already there. We don't have to supply this much amount of oxygen which is already present in the garbage. We will supply only the oxygen need. So we'll subtract this because that oxygen is already present there. So we don't have to supply that much, and whatever is additionally needed, which will be substantial, this will be much less. That's what we need to supply. So you need to be that's again, anything like this, when it comes, you should think, you should not just take things as a face value. You should always try to understand why it is the way it is. So these are the here carbon, hydrogen, sulfur, oxygen, they are the decimal fractions of each of the elements in a kg of fuel on a dry weight basis. So if we can know, so we can I was telling you, you can do the CHONS analyzer. Many labs has it, where you can analyze your garbage sample, and then you can find out this carbon, hydrogen, oxygen, nitrogen, sulfur per kg of the fuel, and then based on that you can plug in those numbers here, and then you can get how much oxygen will be required. So for example, for CaHb, percentage carbon is, we can calculate based on what is the A value, B value, we can calculate this. This formula does take into account the water formed. So that's why water is already been accounted for. So we don't have to worry about that part. In the stoichiometric, we have to account it for separately. So there are so this we'll use this equation, and subsequently in the when we do some math problem, and you will see that again over there. So in terms of how this combustion process works, there are 4 phases. We try to define them in 4 phases. Phase 1 is it is a drying phase. You are trying to dry it. You are making the moisture go away. So moisture go away, what will do? Moisture will go away at what temperature? Slightly above 100 degrees centigrade. So that's why the drying phase goes to around 150, just to have like around, we have to definitely go above 100, so it goes above 150. So moisture is driven off. So in the first phase, we are just getting rid of the moisture. In the second phase, we are volatilization of vapor and gases. So we are taking the temperature to around 700 degrees centigrade, and then we are volatilizing all those vapors and gases, whatever the vapors and gases that is formed. So the volatile components, volatile solids, we measure at what, 550 degrees centigrade. So we have to we take it up to 700, so that all those things which could be volatile will get volatile. Things may get converted to flue gas, get to some of the gaseous component. And then next will be when we heat further, we try to heat it further. So the remaining fixed carbon volatile material, they will partially oxidize, cellulose, lignin, those things will be there. So they will get oxidized further at 700 degree to 1100 degree centigrade. So that's why I said above 1000 you will see most of the time is working. So that's where you have even further burn down of the solid. Then you will have some char. So those remaining charges burn down to bottom ash. So from the char you would get the bottom ash, and this material is our end product of the reaction. And then once it cools down a little bit, this ash is dumped in a dry hopper, the ash receiving system, and then it gets taken away from the main plant, and then it goes to the ash handling system, ash handling part of the plant, where ash will be handled. It could be, ash could be, right now most of the places actually other than Western European countries, this ash is being dumped in the landfill, but there are a lot of work. Even I did a project long back where we use this waste to energy ash as a partial we recovered some of the aggregates, like some of the material from this waste to energy ash, and we used this as a partial substitute for aggregate in road construction. And we did a pilot, we did a lab and pilot, and we saw that it does work up to a certain proportion. We were looking at at what proportion you can mix it, so that the air pollution, so that the leaching is not a problem in terms of the surface water contamination and all. And we found out that it could potentially work. And there are many places in Europe and other where they are actually using that as a partial substitute for road construction now. Our work was done almost 12 years ago. So at that time it was just in a very beginning stage. So we had a paper on that published in a journal. So it's a so this was otherwise if you don't use it, you have to send it to a landfill. But part of that ash could be used. Especially from an Indian context, if you think about, we are thinking we have to have housing for all, isn't it? People are talking about we need to have housing for all by 2020 or 2050, whatever. I think it's 2020. So for housing, we need a lot of raw material. Even to build all these infrastructure, highways, roads and other stuff, we need a lot of construction material. And we know that we don't have that much construction material. We have a lot of problem in sand and all that. We have lots of fly ash from the coal thermal power plant. We have a lot of residual from the coal thermal power plant. We can build this waste to energy plants, and then we will have these residuals from here. And if we separate these different, if we separate the different fractions, remove the heavy metals somehow, or especially the ferrous one can be taken out by using this magnet and all, and then do some environmental risk assessment. That's again essential. Many times we take a waste and we just try to use it for road, we try to use it for other application, and we say, oh, the problem is solved. Problem is solved, but we don't know. It may become a problem in some other area. That's why environmental risk assessment, what is known in the Western world, is a term called beneficial reuse risk assessment. So where we are trying to beneficial reuse this ash, whatever ash, whether from the waste to energy, from coal-based thermal power plant or any industrial waste, when you are trying to reduce the beneficial reuse of waste, you need to make sure that you do a beneficial reuse risk assessment. What does that mean is basically you're looking at the leaching, you look at the total amount of any heavy metals, organics, other things present, whether it will be a problem to environment in terms of the surface water runoff, could potentially have a groundwater problem, it's a soil contamination problem. So those things needs to be looked into. Otherwise what we are doing is we are basically taking a problem at one point and distributing that problem in other area. So that's not really the environmental solution. Ultimately we'll have to go back and fix those problems over time. So we should do this beneficial reuse risk assessment, and that's very, very critical. It's in Indian context, we don't see that much work going on in that area. There needs to be work done in that area. I hope those work will be taken up in a big scale, especially when we are trying to recycle, reuse most of these industrial waste. So let's see. And then we go to the next one. Then there are different types of incinerators. There are in terms of municipal solid waste, you may essentially see two types. Whereas we have two types of incinerator, which is it's a stationary clean. You see that. So municipal solid waste, you mostly see two types of incinerator, two types of MSW incinerator. We have a stationary clean, which is used. It's the first type of waste combustion system designed and used in terms of in the combustion system. Normally we do it for a small quantity. For the small quantity of waste, we can use the stationary clean. Also used for medical waste, can use for pharmaceutical waste, and for R&D purposes like research and development purposes. If you use to have an incinerator, we use a stationary clean incinerator. So what we do, waste is charged into the incinerator and combust it. It passes through the combustion chamber. Ash residue will come out at the last. You will have the ash residue come out. So it's basically a very simple system. Waste is inputted into the incineration, combusted, it passes through the combustion chamber. So there is a combustion chamber. So you think about if you can draw it over here, we have this combustion chamber. So once this waste will travel through the combustion chamber, so the combustion will take place along the length, and so from here, and then finally we'll have the ash coming out. So that's your stationary clean where ash will be taken out. So that's the reaction will take place in this particular area. So So that's one type, and usually done it for the small quantity of waste. And then other one is the rotary clean. Rotary clean will have two chambers. So you see rotary clean is used a lot in cement and other places. You have this rotary clean as well. It consists of two chambers. So there is a primary combustion chamber and there is a secondary combustion chamber. The primary combustion chamber, it's refractory lined. So it's just go back. Okay, it consists of two chambers. So we have it's a primary chamber, which is a primary combustion chamber, which is refractory lined, rotary clean, that is sloped slightly downhill. So you have a slightly downhill, so waste will travel down, and then it also gets rotated as it moves. So things keeps rotated, and the clean is slowly turned at approximately 1 RPM. So it's only 1 revolution per minute. So it's a slow turn. At 1 revolution per minute it is turning, and then the things are the clean is turning at the same time the waste is traveling down. So I'll show you some sketch. I think I have some sketch in next few slides. So waste is turning, waste is also tumbling down, and the clean is rotating at the same time. So and it is getting burned. So it's getting burned, and then you take the secondary chamber we use for the gas phase combustion, because all the gases that is formed in the primary chamber is taken to the secondary chamber and they are burned further at a high temperature. So it's here we can work with a lower temperature, and then we can take it to the secondary chamber where we heat it at a higher temperature. From an energy point of view also it works out to be better, because you save some energy. So the combustion process, the combustion will start at the unloading of MSW trucks into a storage pit. So you have a storage pit usually where the waste will get dumped in from these trucks, and those storage pit will have enough volume to have a volume for waste for 2 days, because say if you have a down for some reason, the plant is not working for some reason, so you don't want to, the waste has to be collected. So you have a storage which can at least handle 2 days worth of waste. And then you have a overhead crane which is used to batch the load waste into the feed, which is the charging chute. So it's basically you have this, if you can draw it here in a small, so that's the, you think about, that's your storage capacity, the waste is over here, and then there is a crane will come down, get the little bit of waste from here, and then it will take it and dump it into the waste incineration part, where all this it will get passed through here where the air will be supplied, and then the garbage will burn in that. And I think I have lots of sketches to explain that. And so the chute will direct the waste to the furnace. The crane can be used to select the different waste to mix the carbon nitrogen ratio. If you have different types of waste, to increase the calorific value, so you want to mix different types of waste. And then the solid waste will land on these grates as they enter the mass fired furnace. The air will be introduced from the bottom, so that's where the air will be pumped in, and then it's below the grates or from the above the grates by a draft fan. This controls the burning rate and the temperature. So the movement of the grates will control the how the garbage will flow down, and in terms of the air supply will control the burning rate, and also the temperature. You need to have an eye on the temperature as well. So once then the gases and the particulate matter, they will be combusted of the organic material, and then they will rise on the combustion chamber where they are burned in excess of 800 degrees centigrade. So this is taken to in another combustion chamber where they will be heated up to 800 degrees centigrade. Then we will have the heat recovery system using the water filled tubes. So you will have the walls of the combustion chamber. So that's the heat exchanger where the heat generated will be taken up by this water. Water will get heated up. So that will become basically produce steam, and that steam will lead to generator, your turbine and all that. Air pollution control equipment will be there where you try to inject ammonia to control NOx. Dry scrubber for SOx and acid gas removal. You have a bag house like a fabric filter for particulate matter. ESP is very popular. You need to have ESP these days as well, electrostatic precipitator. The different categories are there, like 2 fan, 3 fan, different category of electrostatic precipitators are out there which you need to use. And then you will have some ash and unburned material. They will from the grate at the finally it will dump into the residual hamper. So this are mixed together for the ash treatment. So that's those ash could be dumped in a landfill or could be recovered, things could be recovered, as I was trying to explain earlier. So that's the typical design. So let's look at this overall of this particular plant, and then let's try to explain this. So typical combustor design. So here let's go over one by one. So we have the weighing scale where the garbage will weighed in. Why we need this weighing scale? Because we need to know how much waste is coming in, because the collection company will also get paid based on the amount of garbage they are bringing in. So the weighing scale will weigh the full truck, and then they will weigh the empty truck on the way out. So and then they will know the waste of amount of garbage coming in. So this after it comes in, it will get dumped in the waste storage pit. So that's where it gets down here. Then you have this crane which will come down and then collect the waste and then take it and then drop it at this charging chute. So this charging chute is where the reaction starts. So here the reaction is starting, you supply oxygen, and then it comes down, and then this is your grades. So that's where from this point to this point is where you have the reaction taking place, and that's where you are supplying oxygen from the bottom here. So this is where this is called the grades. So these are it's where it can, the grades as of the material, like ceramic material, which can withstand very high temperature. So that's where this is burning. Then you have your secondary combustion chamber. So the gas that is going up, it is even heated up further, so that you have less air pollution issues. Then here is your heat exchanger. These are the tubes which has water. It generates a steam. From the steam it goes to the steam turbine, generator, and electricity. So that part is the energy part. And from here the ammonia scrubber, ammonia injection will control the the ammonia injection will control the NOx. And then you will have here you add lime, you have the dry scrubber, you have the bag house, and then you should have an electrostatic precipitator somewhere now. It has to be there. And then finally the stuff, it's taken all the way to the up, and then things kind of comes off from the stack. So this is how a typical, and this ash can go to a landfill or for recycling or reuse, recycling of ash. So this is typically how the waste to energy system works. Only one major thing which is not there on this sketch is the electrostatic precipitator, which should be part of this air pollution control system, which is a kind of a must these days in all the countries. This is one picture of how this waste to energy plant looks like, any typical factory kind of thing. Another image of showing you the same stuff where you have this waste coming in. It's a self-explanatory, a little bit of more detail here. So crane coming out, the hooper going in, that's where the reaction taking place. Then you have some water walls where that heat exchanger will work, and then the ash, the secondary things are taken up for the ash cleanup over here. So a little bit of different design, but again very similar concept as what you saw earlier. So then this is another picture of some pictures of the waste to energy plant. So here waste coming into the place, and as you can see the waste being dumped in, and that's your crane. If you can see it on your screen, that's the crane which is lifting the garbage, lifting and then dumping it into those grates, and then it gets dumped into here. You can if you can take a closer look, that's where the garbage is burning, and then it's producing the heat which would be used for steam. So this is how it looks like. You have, as I said, it will get input over here, and then it's between this point and this point is when the reaction will take place. The air is added from this section, then some of this gas will be taken into the secondary chamber for further combustion, so that the air pollution is less. And there are different moving bars, fixed bars. We'll talk about that in more detail probably in the next video. We'll talk a little bit more about these grades in a detail, but this is how things really work in terms of the waste incinerator. So bottom line in terms of and this is the grate when it is not working. So this is a ceramic grate, very costly. So this is under maintenance right now. Otherwise, this is the place where you saw all those flames coming out. So this was the place where all those flames were coming out. If you have watched, I think I've told you in the very beginning, if you have watched this Toy Story 3 movie, so at the end of the movie, when you see all the toys taken to that waste to energy plant, that's actually a waste incinerator. and of course that is the two toys comes in and they saves everyone, like our Salman Khan will do it, but similar stuff so that they can make Toy Story 4. Otherwise, if the toys are burned, how will they make Toy Story 4? So, but that's the waste. That was the waste incinerator. So let's. Okay, and this is another type of grate. First you saw like a steps. This is like a roller. Again, same thing here. Rather than using the steps, you can use the roller, and that can be used as well. So different types of things are used. So again, some pictures of a waste to energy plant, closed picture, and the ash has to go to a landfill or can be recovered, and but as likely part of ash does make to the landfill. So let's stop with this, and then we'll continue our discussion in the next video. And so that's I think you had a good understanding of how a typical waste to energy plant works, and what are the different terminologies. The 3 T's are very important: the temperature, time, turbulence, and that's just you should have a good idea about why those are important. That's even important for your exam and for the quizzes. So with this, let's close this video here, and then we'll see you again in the next video. Thank you.